Hello, so in this video I'm going to look at rates of change. Now, rates of change is more or less like calculating the slope of a given function. So, for example, if I look at maybe like the x and y curve or the x and y axis, I have that if I pick a function, okay, so like let's say that we have a function maybe look something like this. Okay, now let's say that we pick a value. So if we were to pick a value, let's say that we just choose one, maybe like right here, and we'll just say that that's going to be a value from A, and then we'll just choose another value. So maybe we'll just choose another value over here, and let's extend this just a little bit. Okay, so that's going to be B. Now, what I can do is I can just form a line between these sets of 2 points. So we have from A to B. And this equation is the y equals f of x. So at this point, one thing that we can do is look at the variation of the delta x, and then we can look at the small variation between delta y. So that's more or less like me trying to find that delta y is divided by, what we can do here is just do delta x, and basically we find that the delta of y is f of b minus f of a, all divided by b minus a. Now, technically this is the formula that you learn like in algebra where you're talking about rates of change or average rate of change. So we'll just put that this is the average rate of change. So what we can look at, for example, is a problem where you just want to find the average rate of change. So for example, let's say that we consider the following equation. S of t equals to negative 16t squared plus 80t. Now, this equation looks at, for example, the height of a projectile if it was thrown upward, and you look at the modeling of the height of the equation. Now, we'll try to make this as easy as possible. So we have S and T. Now the model says that it's from the ground up. So we have that the modeling of the height would look something like this. Now you have that it's in the sky or it's in the air for about 5 seconds. So t is in seconds, and the initial velocity is 80 feet per second. So what we'll do is we'll actually just look at, so let's go ahead and consider like what if we were to look at the following intervals. So let's say that we want to know like what is the average rate of change from 1 to 3, maybe from 1 to 2, and then finally maybe like actually not finally, but we'll do 1.5, and then we'll do not 1 to 1.5, and then we'll do 1 to 1.1. Okay, so quite a bit of computations to do using the average rate of change. Now, in order to do this, we'll basically just have to figure out, for example, like what is S of 1. So S of 1 is equal to, let's see, s of 1 is equal to negative 16 times 1 squared plus 80 times 1, and this gives us the following: negative 16 plus 80, which this is going to give us 64, if I'm correct. So that's going to be 64 feet. So that's the height after 1 second. Now, what we're using is we're using the average rate of change for each of these numbers, 3, 2, 1.5, and 1.1. For the sake of the argument, we'll just look at this as, okay, so you're using s of t minus s of 1 all divided by t minus 1. Now, one way of which that we can look at this is that this is negative 16t squared plus, was it 96 or 80? Okay, so it's 80. Okay, so, right, so we have plus 80t minus 64 feet. But notice that this equation basically tells us that we need to divide by t minus 1. Now, if we plug in, say for example, like 3, we can see like what that's going to give us. But I'm not one for computing like all this stuff, like plug in 3, plug in 2, plug in 1.5, plug in 1.1. But you can try that like for the first one. So like for example, if we use that, this is going to be s of 2. So we're looking for the average rate of change essentially. And this is going to be from the interval from, like this, from 1 to 3. So we have negative 16 times 3 squared plus 80 times 3 minus 64, all divided by 3 minus 1. So we have that this is going to be, and I'm going to do this computation off camera, so 16 times 3 squared plus 80 times 3 minus 64. It gives me 32, so it gives me 32, and this is divided by 2, so this is 16 feet per second. Now, if we go even further to see like what is it for 2, essentially you're going to do the exact same thing. You're going to look at, so we're going to look at the same thing, so average rate, and this is for the time interval from 1 to 2. And we'll do this the exact same way. For example, you'll have negative 16 times 2 squared plus 80 times 2 minus 64, and all of this is divided by 2 minus 1, which is just going to be 1, for example. And I'm going to do this computation again off camera. Plus 80 times 2 minus 64, and that's going to give me, oh, that's strange, it gives me 32. Let me see, negative 16 times 3 squared plus 80 times 3 minus 64. Okay, so 32 is 16. Okay. So in this case, this is going to give me the value of 32. So that means that as we get closer to 1, we're actually increasing the average rate. Now, I'm going to go ahead and use, for example, that if I use the average rate of change, and this is for 1 to 1.5, this is still going to be the exact same process. So you're going to have negative 16 times 1.5 squared plus 80 times 1.5. We'll do it like this, 1.5 minus 64, and then we're just going to divide this by 1.5. 1.5 minus 1. which that's just a half, to be honest, so 0.5. Okay, so again, I'm going to do this computation off screen, just because, I mean, you know that you can plug this into the calculator and then just compute that. So we get that this is going to be 20, which equals 40 feet per second. Okay, so we have one more. Might as well complete it, and then we can look at it in another manner. So we have that the average rate is 1 to 1.1. Now, one way that we can look at this is that the average rate seems to be increasing slightly as we get closer to 1. So we have negative 16 times 1.1 squared plus 80 times 1.1 minus 64 feet, all divided by 1.1 minus 1. Now, if we do the computation again off screen, plus 80 times 1.1 minus 64, hang on, so we have minus 16 times 1.1 squared plus 80 times 1.1 minus 64. Okay, this is a little bit better. So we have that this is going to be 46 or 4.64 divided by 1 point, not 1.1, but 0.01. So this is divided by 0.0, no, that should be 0.1, yeah, that should be 0.1. So we have 0.1, and this is going to give you 46.4. So we have 46.4 feet, okay, so that's 46 feet per second. Now, the question really becomes like, what happens as we get close to 1? And that's actually a very interesting computation, for instance, because essentially what we're saying is that we can find the instantaneous velocity. So we'll just say that, for example, this is the average instantaneous velocity is going to be given by the limit as t approaches 1 of s of t minus s of 1, all divided by t minus 1. Now, if we were to basically kind of like find the limit as t approaches 1, so it's very close, you're going to find that this is going to be negative 16 t squared plus 80t minus 64, all divided by t minus 1. Now, notice that if you were to basically rewrite this in the following manner, you would get negative 16 times t squared minus 5t minus, not minus, but plus 4. And let's see, negative 64. Okay, yes. So this is all divided by t minus 1. Okay, so you might have learned that in taking a limit, like if it's indeterminate, so you notice how you get 1, that's going to give you positive 64 minus 64, then 0 over 0. That just tells you that you need to rewrite the function in a way that you can find what the limit is. So this gives me the limit as t approaches 1 for negative 16 times t minus 4 times, let's see, times t minus 1. And then what happens is that the t minus 1, basically you have that that's going to cancel out. So that's kind of fun. That cancels out. And furthermore, you have that the instantaneous velocity for this is going to be equal to, well, you have the limit as t approaches 1 for negative 16 times t minus 4, which is equal to negative 16 times negative 3, but this is equal to 48 feet per second. So we have that the average velocity, or the instantaneous velocity, is 48 feet per second. Now, technically, you can say that essentially the instantaneous velocity is also the tangent line equal to the limit as t approaches. In this case, we can either say a or b or whatever. So like we can say as t approaches a, and then we'll just say that this is equal to s of t minus s of a, because notice that this is still in the form of the average rate of change, but this is going to be t minus a. But notice that this is actually the secant line, because we have that if we were to choose a value, like back over here where we said that we have, and yeah, this looks a little messy by the way. So yeah, we have that we can pick a value, call it a, and then you fix a value, call it t. So this could be a to t and so on. So what this does, it tells you that the tangent is the same as taking the limit as t approaches a for what we call the secant. So if you want to find the average rate of change, that's the first step. So this right here, this actually denotes what is called the secant. So, you could put that this is the secant, or the average rate of change. And then this part right here, this is what we call the tangent, or the instantaneous velocity. It's all the same in terms of like the vocabulary, so it's all the same, to be honest. So we have that would be the instantaneous rate of change. But there honestly is another way that we can do that. So for example, usually whenever we use the definition of the instantaneous rate of change, we usually will have that there's two forms that we can use for the instantaneous rate of change. So for example, if I was to go back to technically my diagram, and we were to draw the diagram where we have let's say that, okay, yeah, we have a polynomial, and let's say that, for example, that we just want to know what the average rate of change is at this point. So this would be a, and then let's say that we label this as a plus h. Then what that means is that technically I can find my delta x. So delta x is equal to a plus h minus a, which is just h. Right, so then in this case, we find the delta y. Now, in this case, if you look at your equation, so this equation was y equals f of x. That means that the delta x, or the delta y, sorry, the delta y is equal to f of a plus h minus f of a. Now, for those that take, let's say, pre-calculus, you know this as the difference quotient. So what that means is that the instantaneous rate of change is equal to, well, in this case, you want this delta x to be very small. So you would say h approaches 0, and this is going to be f of a plus h minus f of a, all divided by h. So this is going to be your formula as it relates to how do you find the instantaneous rate of change. Well, the answer is that you just use the difference quotient. Yeah, we use the difference quotient. So let me just use this. Okay, So we have that's the formula for the instantaneous rate of change. But you also have that alternatively, like let's say for example that you wanted to just use I don't know, like a simpler equation or formula in finding the instantaneous rate of change. Okay, so the instantaneous rate of change, if you were to essentially like look at maybe a similar polynomial, but if not, then it's all the same if you look at it. So let's say that you're looking at this value, let's say like x, but then let's say that from this ordered pair, you look at a different value, and I'm gonna just pick this one because it's a lot more convenient. Okay, so we can just call this right here b. Now, in this sense, what you're doing is you're forming a line between these 2 points, and that line is basically the secant line. And I'm just going to put like the average rate of change is the m secant. So what that means is that you're looking for the delta x. Okay, so the delta x is basically going in this direction or the other direction, it doesn't really matter. Um, so we can probably just say that, yeah, the delta x, we'll just do it like this. The delta x is equal to, mm, hmm, we can use the definition of b minus x. So yeah, b minus x. But then the delta y, if you look at the delta y is essentially just f of b minus f of x. So that's actually another form that we can use for finding the rate of change. And I guess I should have used an a, but I mean it's all the same. So like if you want to change this to an a, you can, because it's really the same thing because you're trying to figure out like what's the slope of the tangent at this point. But yeah, that becomes a little more difficult, I think. Maybe we can change it. I don't know. Okay, so the whole point is that, yeah, you're finding the slope. And yeah, I think I will change this to a. That way we can say that if we write the alternative, so this is the alt definition, and try not to get confused on me changing the notation because it's all just notation, if anything. Okay, so we have alternate definition. That tells me that the instantaneous rate of change, so the tangent, the slope of the tangent, or this instantaneous rate of change, it's going to be the limit as x approaches a. And we'll do it like this. We'll do f of a minus f of x, all divided by a minus x. Okay, so in this case, it's more or less kind of like the same definition. I mean, we can do the other way around, like f of x minus f of a. So like if you want to write it like that, that's also fine. Like if you prefer kind of like standard to your average rate of change, then this would probably be more ideal, if anything, because you have a minus x. So this gives you kind of like the same thing in terms of like finding the slope of the tangent or the instantaneous rate of change. So we'll just kind of like box this in, and we'll just say that that's going to be the alternate definition. So that's that's not good. Okay, that's a little bit better. Now, if we were to use this alternate definition or this definition of the instantaneous rate of change by using the h value, more or less you would get the exact same thing. So, for example, like if we look at an equation, where we're trying to find the instantaneous rate of change at x equals to, let's say, 2 for f of x equals to, let's say that, for example, that we'll use the following equation. We'll use x squared, but plus 1. Okay, so we want to find the instantaneous rate of change at x squared, well, at x equals 2 for the function x squared plus 1. So I'm going to do where we use our two definitions. So we have that if we write this out, we have the limit as x approaches 2 for f of x minus f of 2 divided by x minus 2. So if we go ahead and we substitute into this equation, we have the limit as x approaches 2 for x squared plus 1 minus, well, we have f of 2, so that's going to be parentheses 2 squared plus 1, and all of this is divided by x minus 2. So this equals to the limit as x approaches 2 for x squared plus 1 minus 5, and all of this is divided by x minus 2. Now, notice that if we go ahead and we use that this reduces to x minus 4, so we have the limit as x approaches 2 for x squared minus 4 divided by 2, well, x minus 2. Notice that basically if you plug in 2, you get indeterminate, you get 0 over 0. So what that means is that essentially you just have to rewrite this as x squared, not x squared, but x minus 2 times x plus 2 divided by x minus 2, which this is the fun part, when things cancel out. So you have x minus 2 cancels out, x minus 2 cancels out. So this basically tells you that the limit as x approaches 2 for x plus 2, well, that's just going to equal to, it's just going to equal to 4. So we have that the rate of change at 2 for this equation is equal to, and that's the tangent, is equal to 4. Now, let's say, for example, that you did it using the other method. So if you did the other method, then you would have that the tangent, and I kind of did it backwards. So we have the limit as h approaches 0 for, well, in this case you have that that's going to be 2 plus h squared plus 1 minus, well, 2 squared plus 1, and all of this is divided by h. Because why? You're trying to make sure that the h is small enough so that you figure out, like, where does that go to. Now, here's where it just gets a little bit complicated, because now you have the limit as h approaches 0 is 4 plus 2h plus h squared plus 1, and this is all going to be minus 5. So what ends up happening is that this is all divided by, let's see, this is all divided by h. So when we simplify this, this gives us the following, and it kind of works out sort of nicely because it tells you that you end up with the ratio of 2h plus h squared is all divided by h. But when you do this, let me see, 4, 5, so minus 5 h squared, this should be 4h actually, so 4h, so this should be 4h So this gives me the following. It gives me that I'm going to have that this equals to the limit as h approaches 0 of 4 plus h, which if we take the limit h to 0, that gives me 4. So essentially I get the exact same thing, but it's really just a matter of preference. Like, do you like having to FOIL, or would you rather just factor? Because that's kind of what I did over here. So it's either or. Now, if you really wanted to, kind of understand the rates of change, it's better to just look at examples where you're dealing with rates of change like negative 16 t squared plus, let's say, like 96t, and then, for example, let's see, minus 16 times 6. Maybe like, for example, like if you had that this was plus 80, for example. So like you have that it was thrown from an 80-foot mark, and from there you're just gonna go ahead and figure out like what's the instantaneous velocity. So, um, for example, if you wanted to find the instantaneous velocity, what you could do is take divided by 32. Let's say, like, for example, like you wanted to know what is the instantaneous rate of change at 3. So technically, you would have to find. Um, okay, so technically, you would have to find um, that you're looking for the limit as t approaches 3, and you have that that's negative 16 t squared plus 96t plus 80 minus whatever the height is for when you plug in 3. And note that this is t minus 3. So what this does is it tells you that you're looking for negative 16 times 3 squared plus 96 times 3 um, plus 80. Okay, so this gives me an equation of 224. So that means that if we plug this in even further, we have that this is the limit as t approaches 3. And for example, this simplifies to negative 16t squared plus 96t. But 80 minus 224 is 144. So we have minus 144. And all of this is divided by t minus 3. Now, in this case, you can factor the bottom portion, and let's see. Okay, so this is going to give you that you have that the limit as t approaches 3 is negative 16 times t squared plus, let's see, nah, that would be minus, right? So that would be minus 96, or minus 6. So minus 6t. And then what is 144 divided by 16? I think it's like 8 or 9. Okay, so 9. So that's going to be plus 9. Now, this is actually pretty interesting because you have that basically this is telling you that the formula, the secant part, is equal to negative 16 times t minus 3. So what that means is that you have that this equals to the limit as t approaches 3 of negative 16 times t minus 3, but that equals to, let's see, that was supposed to be the limit as t approaches 3. So we'll just put approaches 3, and this actually gives you 0. Okay, that's pretty weird that it gives you 0. So there is a way to interpret this, for example, like if we have that we want to find like say for example, like the interpretation of this. So whenever you look at this, you're gonna see that the equation, it looks something like this, of which in this case you have that this is 3, and you have that this right here is about 6 or so. So notice that it gave us that the instantaneous rate of change was equal to 0. But when you kind of interpret this, then in that case you have that essentially that tells you that the tangent, or the rate of change at 3 is 0. So what that means is that technically you found the max height. But then the question would be, for example, like how do you find the maximum height? Well, that's actually just algebra when you think about it. So like you would just have to plug in um, 3 back into this equation and then see like what is the maximum height. Um, let's see. So the highest height would have to be 224 because we actually found it already. We found the instantaneous rate of change is at 3. So in that case, the maximum height is 224 feet. So the logic to this is that once you throw the projectile up in the air, most likely it's gonna reach some highest height of which it's going to be brought down. So, the old saying, like, what goes up must come down. So that's what happens due to gravity. So then it hits the ground after like 6 seconds. And if you want to know, like, also, like, how long is it in the ground or up in the air? Sorry. Okay, so just to kind of recap, you had that there was a formula for secant, or the average rate. Now, sometimes we say that the average is given by f of b minus f of a, and all of this is divided by b minus a. But then you also have that the average instantaneous rate of change. Okay, so if you want to know like what is the instantaneous rate of change, one of the definitions that you could use is the most traditional, like f of x plus h minus f of x all divided by h. Um, and then you have that the other choice is that you can actually just model this like so. Like you have f of x, the limit as x approaches a for f of x minus f of a, and then all of this is divided by not b, but x minus a. Now you do have that, for example, that the notation for some of this is like you're using f prime of a equals to the instantaneous rate of change. So we call this the slope of the tangent, or the derivative at a. So in either case, like as you move into the idea of derivatives and whatnot, then you're actually looking for this notation of f prime of a. Okay. So in the next section, we'll talk about that. But be sure that you do look at some of these examples and how I found the rate